All right, so we were discussing the some important properties of Fourier transform, and the last one was scaling property. Now let's look at another one, which is time shifting. So if f of t has a Fourier transform of f of w, then if I introduce a t0 shift in time domain, this will have an effect of exponential in frequency domain. So we multiply the original Fourier transform with these exponential terms. So the effects of the time shift in frequency is an exponential. In other words, it's a phase shift. So let's have an example. Time domain signal f of t is equal to exponential minus a absolute value of t minus t0. So the question is, can you find the Fourier transform of this signal? And from table 2.7.1 and using the time shifting property that we just learned, let's look at it. Because this is an exponential minus absolute t, let's look at the Fourier transform. Do we have such a signal? Yes, here it is, as you see. This exponential alpha minus alpha absolute t has this Fourier transform. So I just use this result, which is here, has a Fourier transform of this 2a over a square plus omega square from table. And then the question is, if I shift by t0, then it's going to be just multiplication with the exponential term. And the result is the original one was 2a over a squared plus omega squared times these exponential terms. So this is how you can find the Fourier transform of a signal quickly by using the table and these properties. Any question? Okay, then move to the another important property, which is the frequency shifting. So now, if f of t has a Fourier transform of f of w, now we have a shift in the frequency domain. In the previous, we have the shift in the time. Now we have the shift of omega 0 in the frequency domain. So what's going to be the effect in the time domain? It's similar effect, which is the multiplication of f of t with this exponential term, which has a t0. Sorry, omega 0. Okay, to give an example, you guys, use the radio in your car by using the AM modulation. So this is the AM modulation. Actually, you multiplied f of t, which is your signal. In your case, the music that you are listening in your car, times the cosine with the specific carrier frequency. So 1/2 f of t times, remember guys, cosine was equal to this exponential term. 1/2 times f of t exponential j omega 0 t plus f of t times exponential minus j omega 0 t. So if you apply the Fourier transform of this according to this shift is equal to f minus omega 0 plus f minus omega plus omega 0. So in this case, f, what is the W0 is a channel. Like a channel A has an 85.2 megahertz. And the B channel, in this case, the W0 is equal to 97.5 megahertz. So this is how we use this frequency shifting in AM modulation in radio. Okay, So another important parameters, the property is the convolution. This is very important. So let's go over it together. If f1 of t has a Fourier transform of f1 of omega, then f2 of t has a Fourier transform of f2 of omega, then the time convolution is equal to the convolution of f1 with the f2 has a result in f omega times f2 omega in frequency domain. In the time we have the convolution, which is which involves to the integration. Here is just a simple multiplication. Similarly, if we have a frequency convolution, the convolution of f of omega with f2 of omega multiplied by this constant 1 over 2 pi, and it has a corresponding result of f1 of t times f2 of t. So the convolution in frequency domain correspond to the multiplication in time domain. Okay, that was the convolution property. Now, another important property is the time differentiation and time integration. Let's look at this. If f of t has a Fourier transform of f of omega, then the time differentiation, if you take the differential of this signal, is equal to multiplication of j omega times f of omega. Similarly, if you take a integration in time, f of tau d tau, it's equal to division of f of omega with the j omega. Differentiation is the multiplication, integration is division of j omega, plus some of the conditions, initial conditions, and so on. So these are some important property of Fourier transform. Okay, so why we learn the Fourier transform is, of course, we are going to use this Fourier transform so why we use this Fourier transform in LTIC system analysis. If you guys remember, we have a linear time invariant continuous time system. The input is f of t, the system impulse response is h of t, and the output signal is y of t. So the relationship between input and output is governed by this differential equation, where we have the polynomial of q of d and times y of t is equal to p of d times f of t. So in this case, d is replaced with the j omega. So that means if I take a differential with power of k, y of t means is equal to j omega to the power of k times y of omega. So then this is converted to this form, which is q of j omega times y of omega is equal to p j omega times f of omega. So remember this property, y of t output signal was equal to convolution of h of t with the input signal f of t. And this corresponds to this expression, which is y of omega is equal to h of omega times f of omega. Then if I take this h of omega out, which is going to be equal to y of omega over f of omega. In other words, is equal to polynomial p of j omega over q of j omega. And that's equal to h of s. So we just replace the s with the j omega. We can move or convert the h of s to the h of omega. Remember, there was a connection between the Laplace and the Fourier transform when the s is equal to j omega. So if I give you an h of s, by replacing the s with the j omega, you can convert this system function to h of omega. Okay, so then let's have an example for this LTIC system analysis using the Fourier transform. So the question is, I'm given this LTI system which has a transfer function of h of s in terms of Laplace is all equal to 1 over s plus 2. And if the input is signal is f of t in time domain is equal to exponential minus tut. So the question is, can you find the zero state response of this signal under this condition? If you visualize, it looks like this. This is my system transfer function in S domain, which is equal to 1 over S plus 2. And my input signal in time domain is equal to this exponential. And the question is, what is the zero state response? So I'm going to use in the W domain using the Fourier transform. So the y of t has a Fourier transform of y of omega, which is equal to h of omega times f of omega. So in order to find out the y of omega, I need to find the h of omega and f of omega. These are two unknown. Let's start with the input signal, the Fourier transform of input signal. And input signal in time domain was equal to exponential minus tut, which has the f of omega and equal to 1 over j omega plus 1. And you can see from the table 7.1. Let's see. What is it? Is this? Yeah. U of t times exponential minus alpha. Exponential minus alpha t. In our case, alpha is equal to 1. That's why the result is f of omega is equal to 1 plus j omega from table 7.1. We use that pairs. Now, okay, we are done with the f of omega. Next is to find the h of omega. H of s is already given, and we know the connection between the relationship between Laplace and the Fourier transform. Just replace s with the j omega, and we obtain the h of omega, as you see. Just plug into here, and this is the h of omega, which is equal to 1 over j omega plus 2. Now we are ready to multiply, because y of omega was equal to h of omega times f of omega. But what we are asking is y of t. This is the y of omega. And we need to apply the inverse Fourier transform to find the y of t. So what we are going to do is to apply PFE, partial fraction expansion. So I divide into two parts, in two terms, a over j omega plus 1 plus b over j omega plus 2. So you know how to find the PFE. If you apply this PFE, you'll see that a is equal to 1 and b is equal to minus 1. So then the result is going to be 1 over j omega plus 1 minus 1 over j omega plus 2. And from the table 1, we use the same pairs. It looks like this. Now we need to apply the reverse operation. It's going to be equal to, in this case, alpha is 1. It's going to be exponential minus alpha, which is 1 minus t, minus, in this case, alpha is 2, exponential minus alpha is equal to 2t times u of t. This is how you find easily the Fourier transform of a signal. So this is how we use the Fourier transform in order to find the zero state response of the LTIC system. So to summarize, what we learned today is we start with the Fourier transform. And what was the main difference between Fourier transform and the Fourier series? It was that Fourier series only applied to the periodic signals, but most of the signals in practice are non-periodic. Therefore, we use the Fourier transform to apply non-periodic signals. And we introduce the Fourier transform by the definition, as well as the inverse Fourier transform. And we have done some examples for both Fourier transform as well as the inverse Fourier transform. Afterwards, we studied some properties of the Fourier transform, such as duality, scaling, time shifting, frequency shifting, convolution, time differentiation, and time integration. Finally, we show how to use the Fourier transform in system analysis in order to find the zero state response. And we showed an example how to do that. Okay, guys, that's all for today. Any question? All right.